Welcome to the neurology topic of areflexia in deep tender reflexes. So, here today I'm going to discuss about the areflexia and its causes. So, what is it? First of all, it is in deep tender reflex, for example, biceps jerk, triceps jerk, or knee jerk. If it is that and we found there is no reflex present, then this is the areflexia. And clinically, we can diagnose many things from this, or we can get help from this deep tender reflexes if we found any areflexia there. So for understanding areflexia, we need to learn about the pathways of reflex action. Here I'm gonna shortly discuss this part first. So what happens when we perform a deep tendon reflex? What we do is we strike the tendon through a hammer. When we strike this tendon, this part, it transiently increases the length of this muscle. When there is an increase in length, the extrafusal muscle fiber, this one, the longer one, get stretched. When this extrafusal muscle fiber gets stretched, the intrafusal muscle fiber is also get stretched. So first of all, let me tell you about the extrafusal and intrafusal. Extrafusal muscle fiber is the one that actually is a muscle contracting unit which contracts our muscle, and intrafusal is the sensing organ, you can say, or the stretch receptors. So here, when the intrafusal muscle fibers get stretched, it sends signal to spinal cord via 1A fibers. So it sends signal, then from spinal cord, it through alpha motor neuron. It is the efferent pathway through alpha motor neuron. It again innervates the extrafusal muscle fiber, and it causes contraction of this muscle. So when we strike here, this stretch receptor sends this stretching, which transiently overstimulate the alpha motor neuron, this one, which can cause the muscle contraction very fast, leading to positive reflex in deep tendon reflex. For example, if we did not find any reflex, so that means this pathway is any breach in this pathway there is present. So what can be the causes? So I'll come from the periphery, that is from muscle, then neuronal pathway, then spinal cord. I will come from the periphery to center. So what are the causes in the muscle that can give rise to areflexia? So this could be, for example, myopathies. For example, inherited myopathies, for example, Duchenne muscular dystrophy, Baker's dystrophy, and limb girdles, all these things, and also acquired infectious disorder, for example, poliomyositis and dermatomyositis, which are the inflammation of the muscle. This can give rise to areflexia. This is the first one. Then in the neuronal pathways, if this neuron get damaged, then we can get areflexia. For example, mononeuropathy and polyneuropathy. In mononeuropathy, what happens is that only one nerve is getting affected, but in polyneuropathy there is a bunch of neuron that can get affected. And we can see this polyneuropathy in systemic disorders, or for example diabetic neuropathy. We can see that. Then I will come to this part. This is a dorsal root ganglion, but actually it is I wanted to mean that the compress of either the dorsal root ganglion or the nerve roots, when the spinal nerve roots damaged or get compressed, that can give rise to radiculopathy. This can give rise to areflexia. Or for example, radiculopathy or plexopathy, when there is a damage to the nerve plexus. This is the plexopathy. The plexopathy can give rise to areflexia. Then we enter the spinal cord. Here we can see spinal cord lesions which can give rise to areflexia, is that syringomyelia. What is that? This one is the spinal cord central canal, this one. So when there is a dilatation of this part or forming any syrinx here, can push these nerves, can damage here, either via arterial supply damage or via direct damage or damage to the neuronal transmission through axons. So this damage can give rise to areflexia. So syringomyelia is one of the cause. Then extensive myelitis, then spinal cord infarction. We have the spinal arteries here. Any blockage in the arteries or any thrombus can give rise to spinal cord infarction. Then we have intramedullary spinal cord tumors. For example, here any medullary tumor can damage this neuronal pathways. For example, astrocytoma or glioma can damage that. Then we have poliomyelitis. As we know, poliomyelitis, the polio attack the anterior horn cell. So this can give rise to areflexia. Then we have cauda equina syndrome. It is same as the radiculopathy or plexopathy, because here is the same thing. The same pathology is the same. That is the compression of the nerve roots, but it is the most in the distal part of the spinal cord. So when the distal part of the spinal cord get compressed due to either herniated disc or something like that, that can give rise to clinical features like the pain, lower back pain, then sciatica, then loss of bowel bladder control. As we know, the bowel and bladder control is by the sacral plexus or the sacral nerves, so which can get compressed and damaged, and so the patient will complains about loss of bowel and bladder control. Then erectile dysfunction also can be seen. Then we have the Guillain-Barré syndrome that can also give rise to areflexia. Then we have another disorder, that is amyotrophic lateral sclerosis, ALS, which our scientist Stephen Hawking said. So this amyotrophic lateral sclerosis, this can damage both UMN and LMN. But when it damages the LMN or involves the LMN, it can give rise to this part. So this was the overall cause of areflexia. But now I will end the session by discussing another topic, that is this one. That is, we need to know more about the UMN and LMN. It is important. Why? The most important thing is that why there is a brisk or exaggerated deep tender reflexes seen in UMN and why there is a areflexia in LMN. So this is important to know this pathogenesis. So I will discuss about this part. So this is the UMN, this is the cerebral cortex, this is the brainstem, pons, medulla, and this is the spinal cord, and up to anterior horn cell, this pathway is the upper motor neuron. So any damage in this path, and we can see this red one, this red line, this is the reticulospinal tract, which is a descending tract. What it does is that it inhibits the muscle contraction. It inhibits the exaggerated muscle contraction because it have GABAergic inhibitory interneurons which restrict our exaggerated muscle contraction.